All right, here we are with the final video wrapping up not only section 5, but topic 11 as a whole. We're looking at partial pressures and Dalton's law, and what we're going to cover here real quick before we go on to example 11 is how Dalton's law can be used with the ideal gas law. So remember in the last video we said that at constant temperature and volume, as long as those don't change, then pressure and moles are proportional. So what that means is if you were looking at the ideal gas law, whatever you plug in for pressure is going to be what you get for moles and vice versa. So if you plug in the total pressure, you'll calculate number of moles. And the reverse is true. If I plug in number of moles total, I'm going to calculate calculate total pressure. But if I plug in the pressure for just gas A, then what I will calculate is moles of gas A. And if I plug in pressure for gas B, it'll give me moles of gas B, etc., etc. So those two things connect with each other. Now, why is this important? You're going to see in the next example. So let's take a look at example 11. A 1.00 liter vessel contains 0.215 moles of nitrogen and 0.0118 moles of hydrogen at 25.5 degrees Celsius. Determine the partial pressure of each gas and the total pressure in the vessel. Alright, so first thing I like to do, I kind of like to draw a picture, kind of helps me. Alright, so we got this vessel here. I know it's 1.00 liters. I know its temperature is 25.5 degrees Celsius. And what do I know is in there? I know two gases are in there. I know nitrogen is in there, and so is hydrogen. And I know that nitrogen, number of moles is 0.215. And then hydrogen 0.0118. All right. And then that's all I got. Okay, so based on that information, what am I trying to solve for? What's the partial pressure for each, and then what's the total pressure? Okay. Nowhere in this problem does it give me anything regarding pressure. You see that? It doesn't tell me anything. So, total pressure, like before we'd say, oh, let's add up all the pressures. Well, we don't have total pressures. Some of you may be thinking, oh, well, we could add, these two together and get mole fractions. Well, great. You're right, we could get some mole fractions. We could get the mole fraction for nitrogen and the mole fraction for hydrogen because we have enough information. But once you get a mole fraction, what's that going to do? Because to find, not total pressure, to find the partial pressure for each of our gases, let's say I wanted to find the partial pressure for nitrogen, I got to take the total pressure and multiply it by the mole fraction. Well, you don't know what the total is, so you can't find out what the partial pressure is. Do you see there's too many unknowns? So you're sitting here like, oh my gosh, how am I going to possibly solve this problem? Well, we are going to use the ideal gas law. All right, so we're going to use the fact that ideal gas law is PV. I don't know why I'm making the V so small there. PV equals nRT. And here's the thing. Whatever you plug in for number of moles is going to be what you get for your pressure. So if I plugged in the number of moles for nitrogen, for example, that will give me the pressure for nitrogen. And that's your partial pressure that you're trying to solve for. So let's go ahead and do that. Let's get it set up. So first thing I'm going to do is I'm going to rewrite this equation because I want it to be set up to solve for pressure. So I'm going to end up dividing both sides by volume. Okay, and so that gets rid of it there. So my new equation, I'll just get rid of the V here. My new equation ends up being pressure equals nRT over V. And if I'm going to plug in the number of moles for nitrogen, that will get me the partial pressure for nitrogen since they relate to each other, right? So what's my number of moles for nitrogen? It's 0.215. All right, my gas constant R is 0.08206. I'm going to be really bad and not write the units because I'm running out of space. And then my temperature, it's 25.5 degrees Celsius, but that needs to get converted to Kelvin. So if I were to add that, it would be 298.65, but I'm going to round it to 7 because of the 1 decimal place. So 298.7 Kelvin. No space. And then divide it by the volume, which conveniently the volume is 1.00 liters. That's nice. So what would be my pressure for the nitrogen gas? Well, I would take 0.215 moles, times it by 0.08206, and then times my temperature, 298.7 Kelvin, obviously divided by 1 is going to be the same. So my pressure with 3 sig figs is what? 5.27. And what's going to be the pressure? It's going to be atmospheres, right? Because we're using the ideal gas law, so that's the unit of pressure. So that is the partial pressure of just the nitrogen. Here's the thing, we're going to do the exact same thing, but now we're going to do it for hydrogen. So to figure out the partial pressure for hydrogen, I need to plug in the moles for hydrogen times R and T, and then divide it by V. So my moles for hydrogen is 0.0118. Gas constant is 0.08206. That's still the same. Temperature is still the same, 298.7 Kelvin. And then volume is still the same. So the only thing that's changing is the number of moles. So 0.0118 times 0.08206 times 298.7 divided by 1. My partial pressure for just the hydrogen is going to, with 3 sig figs, is 0.289 atmospheres. And you may be thinking, wow, that's really a lot lower than the pressure for nitrogen. You're right, because notice the moles is a lot lower than the nitrogen. So that makes sense. So finally, how are we going to solve for what's the total pressure? Now that you have the partial pressures for both nitrogen and hydrogen, all we have to do is add them together. So the total pressure of this entire system is 5.27 plus 0.289. And so that's going to give me, with correct sig figs, because it's got to be 2 decimal places is the lowest between those, 5.56 ATM. So I was kind of all over the place with my calculations, but hopefully that made sense. There we go. So that would be our answers there. All right, this last couple slides, we're not going to solve anything. I just want to kind of explain the application. So this was put in the notes because we would normally be doing a gas laws experiment in the lab. And so I like to explain this in lecture so you're aware. But like I said, we're not doing the gas laws lab. And so I just want to kind of talk about this idea in a conceptual way. So let's say you were doing an experiment, some sort of reaction in this Erlenmeyer flask, and let's say this experiment produces a gas. So the gas would be up here, but remember, gases will fill their container. So what it ends up doing is it ends up filling this tube, going all the way through, going in here, and then pushing its way, okay, to go through here. And it would end up actually collecting up here. And the reason why we do that is so that we can measure the pressure. But what gas is up here, right? What gas is in this area? Well, obviously the gas that you created in the reaction, okay, that's going to be up there. But also, since there's water right here, there's also going to be a little bit of water vapor that's also going to be up here. So up here, you actually have a mixture of gases. You have the gas that you produced in the reaction, but you're always going to have a little bit of water vapor in there as well. There's some water molecules that are also contributing to the pressure because they're in the gas phase. And so to figure out what the gas is for just that what was being created, you'd have to subtract out the pressure of water. Okay, and so the idea, all I want you to understand from this slide is when you collect the gas up here, it's not just the gas that you produce. There's also a little bit of the water vapor. That's really all I need you to know. We're not going to go too much more into depth than that. That was just to get you prepped for, when we would go to the lab and do the experiment. All right, well, that wraps it up for topic 11. So we'll see you in topic 12.